Okay, in section 4.4 we learned how to graph sine and cosine curves. We learned about some characteristics such as amplitude, period, frequency, and we're going to carry that on to now tangent, cotangent, secant, and cosecant in section 4.5. The tangent function, as you know, is sine of x over cosine of x, which is great because when sine of x is positive, when we know that, or I'm sorry, when sine of x is 0, which we know from the unit circle, tangent is 0 because 0 divided by anything is still 0. So we can see that when the sine curve, the dashed one, is 0, we have a tangent value is also 0. When the cosine curve, which is the denominator of the tangent function, is 0, when you divide by 0, it's undefined, so tangent would then provide a vertical asymptote. Sound familiar? So, everywhere cosine is 0, or crosses the x-axis, tangent has a vertical asymptote. I also like to throw in a couple other points which I've nicknamed corners, just because those are the easy ones. The tangent of pi over 4 is 1, so that's an easy point to work with. It's not like square root 2 over 2 or square root 3 over 2 or whatever the other messy ones are. So in lining up our first graph of the tangent curve here, I'm going to start with the x value negative pi over 2. And then continue on by pi over 4 to cover the values, the important values from negative pi over 2 to pi over 2. The reason I'm doing that is because the period of a tangent curve is only pi. It only takes half of a circle, pi radians, to go through one period of the tangent curve before you start repeating. So the period is pi. I can repeat this pattern following every center point, 1, 2, 3, 4. So at 0, pi, 2 pi are all going to be center points. Same with negative pi and negative 2 pi. Now these points that I have nicknamed corner points are going to have the same relative position as those center points. So they're going to be the one to the right is at positive 1, the one to the left is at negative 1. The one to the right is at positive 1, the one to the left is at negative 1, etc. Also, the asymptotes are going to occur every pi units. So I'm going to draw in a couple more of those. And finish what is going to be about 5 periods of a tangent curve. Now, the domain of a tangent curve is weird because there's infinitely many values left out of it. Now, your book has a way of showing the pattern of the values that is left out. I'm going to ask you to show me the pattern by listing 3 of the values. So, for example, negative pi over 2 is the first one, pi over 2 is the second one, but then there's a pattern. The next one occurs out here at 3 pi over 2. The following would be at 5 pi over 2. Or if we wanted to go backwards, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. Now any series of 3 values is perfectly acceptable. I typically use negative pi over 2, and 3 pi over 2 just because they're the values I worked with in initially graphing the tangent curve. The frequency is the reciprocal of the period. In other words, 1 pith of this curve is going to occur between 0 and 1. The amplitude of a tangent curve, well, the tangent curve doesn't have an amplitude because it's infinitely tall. So to measure infinitely tall is ridiculous. So if I ever give you anything that says amplitude for a tangent curve, you just leave it blank. It does not have an amplitude. The tangent curve has infinitely many n behaviors. The limit as x approaches, let's say pi over 2 from the left, is positive infinity, and the limit as x approaches positive pi over 2 from the right is negative infinity. Now technically that will happen for every single one of those asymptotes. So the same exact values you've left out of the domain. Now in this tangent curve, the directions have asked us, this is example 1 in your book, the directions have asked us to describe y equals negative tangent of 2x in terms of the basic function? Well, the basic function is tangent. So y equals negative tangent 2x is the graph of tangent of x after a horizontal shrink by 1/2 and a vertical flip over the x-axis. So in calculating each of those, for the basic points of a tangent curve, the tangent of a negative pi over 2 is undefined, negative pi over 4 is negative 1, etc. I'm going to take each one of these points and put it through the two transformations in this curve. So the x-coordinate of negative pi over 2 has now been shrunk in half. So that will be x equals negative pi, oops, that's one too many things, pi over 4. Then the vertical flip over the x-axis only affects the y-coordinate, so it's going to stay negative pi over 4, x equals negative pi over 4. I am taking the x-coordinate and multiplying by 1/2, and then I'm taking the y-coordinate and changing from negative to positive or vice versa. So this will be negative pi over 8, negative 1, and this will be negative pi over 8, positive 1. Nothing is going to happen to the center because if you multiply or change from positive to negative, zeros don't change. Let's see, this will be positive pi over 8, comma, positive 1, and then pi over 8, negative 1. And this horizontal vertical asymptote will change x equals pi over 4. And then again, the vertical flip doesn't affect it. Now I've pre-graphed that for you here. I did not change the scale on my x-axis. I could squeeze in this enough. It's getting a little small. I probably could have expanded out my axis a little bit, but I didn't. Now, the domain values left out here. Well, the two asymptotes we got were negative pi over 4 and positive pi over 4. So then continuing with that pattern, I see 3 pi over 4, 5 pi over 4. So again, you can pick any 3 values you want as long as you show that this is an infinite pattern with your 3 dots in the front and 3 dots in the back. So I can pick pi over 4, 3 pi over 4, 5 pi over 4, dot, dot, dot. The period of a normal tangent curve is pi. Now this has been horizontally shrunk in half, so this is going to be pi over 2, which leaves the frequency at 2 over pi. Now the asymptotes, this is something we didn't talk about on the previous page. Asymptotes, again, are infinite, so you've got to demonstrate that pattern with dot, dot, dot. You can pick the same exact values as your domain, but because it's an infinite pattern, you can pick different values that just fall in that same pattern. So to spice things up a little bit, I'm going to pick negative 3 pi over 4, negative pi over 4, and positive pi over 4. See what I mean? Math is exciting. Now on the bottom right, examples of my end behavior. I chose 3 pi over 4. So here's 3 pi over 4. As we approach from the left, the y values go down to negative infinity. As we approach from the right, the y values go up to positive infinity. Any questions? Just kidding, this is a video, I can't answer questions. Alright, this last page would be an example that you would do in your homework. I've been doing a little bit more work than your homework would require you, just because I want to get as much information out to you as I can. But you are only required to do what the directions ask you in your homework, so that's what I'm going to demonstrate on this problem. Describe the graph of the function in terms of a basic trig function. Well, the graph of y is the tangent of x horizontally shrunk by 1/2. Locate the vertical asymptotes and graph 2 periods of the function. Vertical asymptotes of tangent are at negative pi over 2, pi over 2, 3 pi over 2 when cosine the denominator is 0. So the vertical asymptotes of the tangent of 2x, which is vertically shrunk in half, are at x equals negative pi over 4, pi over 2, and 3 pi over 4. Each one of those values shrunk in half, so they're closer together. Here are my 2 periods of the curve found by the points and asymptotes I got by translating the original tangent values. And I followed that pattern once to draw exactly 2 periods of the function, which the directions ask for. Now, the cotangent curve, or the cotangent function, excuse me, has very, very similar characteristics to the tangent function, as you know, because it's just the reciprocal. So when so cotangent is cosine over sine. So when cosine, the numerator, is 0, now the cotangent function will be crossing through the x-axis. And when sine is 0, we have an undefined value for cotangent, so we have asymptotes in the cotangent function. So again, we have, let's see, this is going to be an asymptote because the cotangent of 0 is undefined. So x equals 0 is our first vertical asymptote. The cotangent of pi over 4 is positive 1. Okay, the cosine of pi over 2 is 0 divided by the sine of pi over 2 is 1, which is 0. This corner, the tangent of 3 pi over 4, is negative 1, and then the cotangent of pi is again undefined, so we have another asymptote, x equals pi. And I've drawn those asymptotes in, I've followed the patterns, I've labeled at least a period's worth of asymptotes and corner points along with a center, so 5 things in one period: asymptote, corner, center, corner, asymptote. The domain follows the same strategy as tangent. I have to name 3 values that I've left out in a infinite pattern form. So ... negative pi, comma 0, comma pi, comma ... The range again is all real numbers. Period, basic cosine or cotangent function is pi. Frequency is going to be 1 over pi, and the asymptotes I have found are the same values I'm leaving out of the domain, so that will be ... negative pi, 0, pi ... And again, I've left some sample end behaviors here for your review later. Now this guy has a lot of transforming going on. We've got, let's see, well, the function is the cotangent of x after a horizontal stretch by 2, that's the x over 2, which is really instead of dividing or shrinking by 2, you're actually stretching it by 2. A vertical stretch by 3, and a vertical shift up 1. So that's what my description is here. So I use the basic cotangent values of x equals 0 for the asymptote, because when you plug in 0, the cotangent value is undefined. Pi over 4, comma 1, pi over 2, 0, etc. And I horizontally stretched each by 2 by multiplying the x-coordinate by 2, vertically stretched by 3 by multiplying the y-coordinate by 3, and then vertically shifting up 1 by adding 1 to each of the y-coordinates. So I get the values, the final values here. I have plotted those, I have labeled them, I have drawn my really stretched out cotangent curve, and now it's pretty easy for me to identify the domain. It's all real numbers except negative 2 pi, 0, 2 pi, ... The range is all real numbers. The period of a basic cotangent curve, like tangent, is pi, but this has been horizontally stretched out to be twice as big, so now it's 2 pi, which means the frequency is 1 2/π. The asymptotes are going to be, again, you can pick the same values that you left out of the domain or just something within that pattern. So I could have put ... 0, 2 pi, 4 pi, ... And then again, some example end behaviors left for your review. Here's an example very similar to what you'll see in your homework. For cotangent, again, I've done just the basics of what you would be required to do by following the directions in your homework. I've described how the cotangent function is related to number 9. I have described where the vertical asymptotes are. I have then graphed exactly 2 periods of the function, making sure to label a period's worth of asymptotes, center points, and corners.